Right now, as you read these words, there is a storm of invisible activity inside your brain. 86 billion neurons ignite in shimmering cascades, forming patterns of thought, memory, and awareness. For centuries, scientists and philosophers have tried to explain how this symphony of electrochemical activity gives rise to consciousness itself. Some believe it is nothing more than computation, the firing of circuits producing an illusion of self. Others suspect that something deeper is at play, that consciousness may be woven into the very fabric of the universe through quantum mechanics, the physics that governs subatomic particles. It is here, in the meeting of neuroscience and quantum theory, that one of the most audacious ideas in modern science emerges, that your mind may not simply exist within your skull, but instead may be directly entangled with the universe. The story of this theory begins with a mathematician, Sir Roger Penrose, renowned for his groundbreaking work in cosmology and relativity, was troubled by a philosophical puzzle that haunted him for decades. Classical physics, he argued, could not explain the phenomenon of human understanding. Computers can calculate with flawless precision, but they do not understand. He believed that consciousness was not algorithmic, not reducible to the mechanical operations of neurons. To Penrose, the human mind tapped into something that transcended computation, and the only candidate grand enough to explain it was quantum mechanics. Quantum theory, after all, defies the rules of everyday logic. Particles exist in multiple states at once until observed. Entangled particles mirror each other's behavior across vast distances. The act of measurement alters reality itself. For Penrose, these features of quantum physics offered a path toward explaining the mystery of awareness. He imagined that within the structures of the brain, quantum processes could create the subjective experience of consciousness. Yet there was a problem. Penrose was not a neuroscientist, and the human brain is not a blackboard of equations, but a labyrinth of cells, proteins, and chemical signals. To transform his philosophical speculation into a scientific theory, he needed an ally who understood the biology of consciousness from the inside out. That ally appeared in the form of Stuart Hameroff, an anesthesiologist. For decades, Hameroff had studied how consciousness can be switched off and on with a single dose of anesthetic gas. He knew that certain chemicals could render a patient entirely unconscious, and yet leave the body's vital functions untouched. To him, this suggested that consciousness was not merely the sum of overall brain activity, but rather localized in fragile, microscopic structures sensitive to disruption. His fascination settled on microtubules, tiny protein scaffolds inside neurons that maintain their shape and help transport molecules. These structures, Hameroff believed, could provide the biological substrate for Penrose's quantum processes. Together, Penrose and Hameroff developed the orchestra, or theory, short for orchestrated objective reduction. They proposed that microtubules inside neurons sustain quantum states, and that when these states collapse, they generate moments of conscious experience. According to orchestra, or consciousness is not a continuous stream, but a rapid series of quantum events, stitched together into the flowing awareness we perceive. This theory was electrifying, drawing attention from scientists, philosophers, and the public alike. But it also provoked fierce criticism. Physicist Max Tegmark of MIT delivered one of the sharpest blows. Using calculations, he argued that the brain is far too warm and wet for delicate quantum states to survive. Quantum coherence, the phenomenon of particles existing in superposition, decays in trillionths of a second in biological environments. Consciousness, by contrast, unfolds over milliseconds, billions of times longer than quantum effects could last. Tegmark likened orchestra, or to building a sand castle in the middle of a hurricane. The quantum states would collapse before they could play any meaningful role. For many in the scientific community, this critique seemed decisive. Yet the idea refused to die. Quantum consciousness theories tapped into a mystery that classical neuroscience could not fully solve: the hard problem of consciousness. Why should information processing in the brain feel like something from the inside? Why is there a subjective experience of red or pain or love? A purely mechanistic brain might process inputs and produce outputs like a computer, but it is difficult to see why this should generate inner awareness. Orchestra, or offered an answer. Consciousness arises not from classical computation, but from quantum events woven into the universe itself. The debate intensified as new evidence emerged. In physics laboratories, experiments showed that quantum effects could appear in unexpected places. Photosynthesis, bird navigation, and even enzyme reactions seemed to rely on quantum coherence. If plants and birds could harness quantum mechanics in biological systems, could the brain do the same? Critics countered that these processes occur under specialized conditions, shielded in ways that neural tissue could not replicate. The brain, bathed in a noisy soup of ions and chemicals, seemed hostile to fragile quantum states. Still, the discoveries kept the door open, suggesting that evolution may have developed mechanisms for protecting quantum processes in unexpected ways. By the late 1990s and early 2000s, the conversation around orchestra had shifted from outright dismissal to cautious curiosity. Some researchers began investigating whether quantum error correction, mechanisms that protect information from environmental noise, might exist in living organisms. Certain bacteria, for example, appear to use quantum coherence in navigation, raising the possibility that biological systems can indeed shield fragile quantum states. If bacteria could do it, perhaps brains had evolved even more sophisticated strategies. Meanwhile, philosophers seized on the implications. If consciousness emerges from quantum mechanics, then it may not be unique to humans. Panpsychist thinkers argued that consciousness could be a fundamental feature of reality itself, present in all matter in primitive form. Your unified awareness, they suggested, could be the product of quantum entanglement weaving together countless tiny conscious elements. Such ideas stretched the imagination, yet they also resonated with ancient intuitions that mind and cosmos are inseparable. At the same time, the quantum consciousness debate began to influence other frontiers of science. In artificial intelligence, the question loomed: if consciousness is classical computation, then advanced AI should eventually become conscious. But despite rapid progress in machine learning, no computer shows convincing signs of subjective awareness. If consciousness depends on quantum processes, then building a conscious AI would require mastering quantum computing in ways far beyond today's systems. This tension sharpened the contrast between intelligence and awareness, suggesting that the two may not be synonymous. As neuroscientists probed deeper, tantalizing clues began to surface. In 2013, researchers at Cambridge University discovered evidence that quantum effects might persist in brain tissue for far longer than expected. Using advanced laser spectroscopy, they observed coherence in protein structures within neurons, even at normal body temperature. This finding sent ripples through the consciousness research community, raising the possibility that the brain's molecular machinery might indeed support quantum phenomena. Still, the controversy raged on. Skeptics dismissed such findings as experimental artifacts, the product of noise or misinterpretation. Advocates countered with increasingly sophisticated arguments, pointing to new data and refined models. The debate revealed not only the difficulty of studying consciousness, but also the strangeness of quantum physics itself. At the heart of the mystery lies the observer effect. Quantum systems behave differently when measured. If consciousness is entangled with quantum processes, then studying it may be like trying to measure water's temperature with a thermometer that changes the water itself. And so, the theory of quantum consciousness remains suspended between bold speculation and tantalizing evidence. It challenges the mechanistic worldview of classical neuroscience, while confronting the profound enigma of subjective experience. Whether orchestra is correct or not, its influence is undeniable. It forces us to question what it means to be conscious, and whether our minds are isolated phenomena or reflections of a deeper cosmic reality. The controversy surrounding quantum consciousness has always balanced precariously on the edge of science and philosophy. On one side stand the critics, who insist that invoking quantum mechanics to explain the mind is little more than mysticism cloaked in scientific language. On the other side are proponents who argue that the most extraordinary phenomenon in the known universe, subjective experience, demands an equally extraordinary explanation. Between them stretches a battlefield of evidence, speculation, and the stubborn mystery of what it means to be aware. Among the most forceful criticisms comes from the physics community. Max Tegmark's calculation that quantum coherence in the brain would last no more than a 10/trillionth of a second struck like a hammer blow against the orchestra or hypothesis. To him, the proposal that microtubules sustain quantum states long enough to generate conscious thought was implausible. Conscious experience unfolds in milliseconds. Millions of times slower than quantum coherence would survive in the brain's chaotic environment. This mismatch seemed insurmountable. Tegmark compared it to trying to build a sandcastle in the middle of a storm. The delicate structure would be swept away long before it could form. Such arguments carry weight, because the laws of quantum mechanics are merciless in the face of environmental interference. Decoherence, the process by which quantum superpositions collapse under the influence of their surroundings, is a fact of life. Quantum systems in laboratories require near absolute zero temperatures and meticulous isolation to survive. By contrast, the brain operates at body temperature, bathed in ions, neurotransmitters, and electromagnetic fields. From a physicist's perspective, the idea that fragile quantum states could endure in such a storm seems fanciful. Yet critics often overlook a simple point. Biology has repeatedly demonstrated an uncanny ability to exploit improbable processes. Photosynthesis, for instance, relies on quantum coherence to transfer energy with near-perfect efficiency. Birds appear to navigate across continents using quantum entanglement in proteins sensitive to Earth's magnetic field. Enzymes accelerate chemical reactions in ways that seem to harness quantum tunneling. These discoveries remind us that life is not a passive bystander, but an active engineer, capable of evolving mechanisms that defy expectations. If bacteria can use quantum error correction to protect coherence, why should the brain be any less ingenious? This question takes on even greater urgency when viewed through the lens of psychiatry. For decades, treatments for mental illness have targeted neurotransmitters, chemicals like serotonin, dopamine, and norepinephrine. Antidepressants, antipsychotics, and mood stabilizers all function by altering classical chemistry. Yet their success is limited, often producing only partial relief, and sometimes none at all. What if these disorders originate not at the chemical level, but at the quantum level of brain processes? If consciousness arises from quantum activity within microtubules, then disruptions in these processes might produce conditions such as depression, schizophrenia, or bipolar disorder. This idea is no longer confined to speculation. Some researchers suggest that therapies like transcranial magnetic stimulation, which use magnetic fields to influence neural activity, might actually affect quantum states in neurons. Meditation, long known to alter brain function in mysterious ways, could be stabilizing quantum coherence. Even psychedelic substances, capable of inducing radical changes in perception and self-awareness, might act by modulating quantum processes. If true, then the path to mental health may not lie only in balancing chemicals, but in mastering the hidden quantum machinery of the mind. Still, the evidence remains fragmentary. For every tantalizing finding, there is a counter-argument. When researchers observed coherence in brain proteins at normal body temperature, skeptics quickly pointed out that the results might be artifacts of measurement. When artificial neural networks unexpectedly exhibited prolonged quantum coherence, detractors argued that these were experimental anomalies rather than insights into consciousness. The debate is littered with claims and counterclaims, each side accusing the other of methodological flaws. But perhaps the deepest reason quantum consciousness theories persist is that classical neuroscience still cannot answer the most haunting question: why does any of this feel like something? This is the so-called hard problem of consciousness, articulated most famously by philosopher David Chalmers. Information processing explains how inputs lead to outputs, how neurons fire and circuits activate. But none of it explains why pain hurts, why red looks vivid, why music stirs the soul. Subjective experience, qualia, remains unexplained. If the brain is nothing but a biological computer, then in principle, sufficiently advanced machines should eventually become conscious. Yet despite astonishing progress in artificial intelligence, no computer has ever shown convincing signs of genuine subjective experience. They analyze data, generate language, even create art, but they do not feel. The difference between a machine calculating and a person understanding is vast, and it is here that orchestra or claims to offer an answer. Consciousness is not the byproduct of computation. It is the result of quantum processes embedded in the universe itself. This has profound implications not only for neuroscience, but also for philosophy and ethics. If consciousness is rooted in quantum mechanics, then it may not be limited to humans at all. Panpsychism, the idea that consciousness is a fundamental feature of reality, finds a natural ally in quantum theories of mind. Under this view, even elementary particles might possess primitive forms of awareness, which combine through entanglement to form complex experiences like our own. Your unified consciousness could be the emergent harmony of billions of quantum notes resonating together. Such a perspective transforms our understanding of existence. We are not isolated observers in a meaningless universe, but participants in a vast web of consciousness. The brain, then, is less a generator of awareness and more a receiver, a resonant structure tuned to the frequencies of quantum reality. This resonates with spiritual traditions that have long intuited that mind and cosmos are inseparable, that awareness is not an accident of biology, but a fundamental feature of existence. Yet the scientific community remains divided. Some physicists and neuroscientists see orchestra or as an elegant but untestable speculation, more philosophy than science. Others point to emerging experimental techniques, such as studies of entanglement in neural tissue, as the beginning of a new frontier. The controversy is unlikely to end soon, because at its heart lies not just a technical dispute, but a philosophical rift about the nature of reality. The double-slit experiment, one of the most famous in physics, underscores this tension. When electrons are unobserved, they move through two slits simultaneously, creating an interference pattern. When observed, they behave like classical particles, collapsing into a single path. The implication is unsettling. The act of observation changes reality. If consciousness is involved in this collapse, then awareness itself might be a fundamental actor in the unfolding of the cosmos. Some argue that this interpretation is a stretch, that quantum mechanics only describes probabilities, not consciousness. But the coincidence remains. The universe behaves differently when observed. In this way, the quantum consciousness debate is more than a clash of theories. It is a struggle over meaning, over the place of the mind in the universe. If consciousness is classical, then we are machines sophisticated, but machines nonetheless. If it is quantum, then we are entangled with the fabric of reality, participants in a cosmic process far greater than ourselves. Either way, the question forces us to reconsider everything we thought we knew about who we are. In laboratories across the world, researchers began to chase whispers of evidence that consciousness might truly rest upon quantum foundations. For decades, the main objection had been simple. Coherence could not survive in the brain's noisy environment. Yet biology has a way of surprising us. In the early 21st century, experiments began to suggest that quantum effects might persist in places once thought impossible, forcing scientists to reconsider their skepticism. At the University of Cambridge, neuroscientist Elena Vasquez made a discovery that shook the field. She was investigating how neurons process signals when she employed advanced laser spectroscopy to probe protein structures within brain tissue. To her astonishment, she detected quantum coherence lasting far longer than any theory had predicted possible under normal physiological conditions. Instead of collapsing instantly, the quantum states seemed to linger, defying expectations that decoherence would obliterate them in trillionths of a second. This was not a sterile laboratory setup at absolute zero. It was messy, living tissue at body temperature, surrounded by ions, fluids, and electromagnetic noise. If coherence could endure here, then perhaps the brain was not as inhospitable to quantum mechanics as Tegmark's hurricane analogy had implied. Skeptics responded quickly, warning that the results might be artifacts of the measurement process, illusions created by the very tools designed to observe them. They reminded the community that biology is full of complex signals, and distinguishing genuine quantum effects from experimental noise is notoriously difficult. Yet Vasquez's work was not an isolated outlier. Around the same time, researchers studying photosynthesis, bird navigation, and enzyme catalysis were uncovering undeniable evidence of quantum behavior in biological systems. Plants appeared to use quantum coherence to transfer energy with nearly perfect efficiency. Birds seemed to rely on quantum entanglement in proteins to sense Earth's magnetic field. Enzymes achieved reaction speeds that classical chemistry could not explain without quantum tunneling. Taken together, these findings build a case that life has not only tolerated quantum mechanics, but actively harnessed it. Evolution, with billions of years of experimentation, may have learned to use fragile quantum states as tools for survival. If a bacterium could do it to guide itself toward nutrients, why should the human brain, evolution's most complex creation, not do something similar for consciousness? The evidence was not confined to natural biology. Artificial systems began producing results that defied prediction as well. Scientists building neural networks to mimic the architecture of brain tissue found that their synthetic models sometimes exhibited spontaneous quantum coherence. These artificial networks were not designed to study consciousness. They were built to understand quantum information flow. Yet, unexpectedly, coherence in these systems lasted far longer than any calculation had suggested possible. Even more puzzling, the coherence did not simply fade away, it stabilized, as if the networks themselves were finding ways to preserve it. This hinted at the possibility that certain architectures, biological or artificial, may naturally protect quantum states in ways we have yet to understand. The implications for consciousness were profound. If artificial structures could exhibit quantum coherence beyond theoretical limits, then perhaps the brain's microtubules had evolved mechanisms to do the same. The line between biology and technology blurred, as if both were tapping into deeper laws of physics. This suggested that consciousness might not be an accidental quirk of neurochemistry, but an emergent property of quantum information processing. Around this time, researchers began exploring the idea of quantum error correction in living systems. In computing, error correction preserves fragile information by encoding it redundantly, allowing systems to recover from disturbances. Some bacteria appeared to use similar strategies, protecting coherence as they navigated. If bacteria could evolve quantum protection mechanisms, could the human brain have refined such strategies to sustain conscious awareness? The possibility was tantalizing because it offered a way to bridge the gap between Tegmark's critique and Orch's claims. Quantum states may be fragile in principle, but biology might have found ways to shield them. Experiments soon turned toward direct tests of quantum entanglement in brain tissue. If Orch was correct, then different regions of the brain should exhibit quantum correlations that cannot be explained by classical physics. Early results hinted at exactly this possibility, though the findings were controversial and difficult to replicate. The technical challenge of distinguishing true entanglement from mere statistical coincidence is immense, and each experimental setup introduces assumptions that can skew results. Yet the fact that these studies were being attempted at all marked a shift. Quantum consciousness had moved from philosophical speculation to a field of testable hypotheses. As evidence accumulated, the debate spread beyond science into philosophy. If coherence and entanglement exist in the brain, then what is the role of subjective experience? Some argued that these quantum processes might explain the brain's astonishing computational power. Classical computers struggle to perform even a fraction of the tasks your brain handles effortlessly, processing vision, language, memory, emotion, and self-awareness simultaneously, all while consuming less energy than a light bulb. Quantum systems, by contrast, can solve certain problems exponentially faster by exploring multiple possibilities at once. Perhaps the brain's efficiency could only be explained by quantum computation. But critics were quick to counter. Evolution, they argued, is an unparalleled optimizer of efficiency. If quantum processing provided such an overwhelming advantage, why are its effects so subtle and difficult to detect? Wouldn't evolution have left clearer fingerprints of quantum exploitation in the brain? To them, the difficulty of finding definitive evidence suggested that quantum processes, if present at all, play only a minor role in consciousness. The debate then veered into philosophy. If consciousness is quantum, then it may be woven into the very structure of the universe. Panpsychist thinkers embrace this view, suggesting that consciousness could be present at every level of matter, combining through entanglement to form the rich experiences of human life. Your stream of awareness, under this lens, is not generated in isolation, but emerges from a vast ocean of universal consciousness. The implications were staggering. Consciousness would no longer be a late evolutionary accident, a quirk of neurons, but a fundamental feature of reality itself. The mind would not merely exist within the universe. It would be a reflection of the universe's deepest structure. Awareness would be the cosmos knowing itself, localized for a time in the patterns of your brain. Even more startling were the echoes this idea found in ancient traditions. Philosophies from East and West have long spoken of a unity between self and cosmos, of a universal consciousness that individual minds participate in. Quantum theories of consciousness seemed, at least metaphorically, to converge with these insights, offering a bridge between modern science and ancient intuition. Whether this convergence is genuine or coincidental remains debated, but its allure is undeniable. Yet, for all the fascination, the question remains unresolved. Experiments continue to produce intriguing but ambiguous results. For every claim of coherence or entanglement in brain tissue, there are challenges of replication and interpretation. The tools to measure such delicate phenomena in living systems are still crude compared to the complexity of the brain. The controversy seems destined to persist until new technologies provide definitive answers. In the meantime, the debate continues to shape how we think about ourselves. If consciousness is quantum, then it is not confined to biology. It may be possible to create artificial consciousness by building machines that exploit quantum mechanics. If consciousness is classical, then no matter how advanced our computers become, they will remain clever zombies, mimicking awareness without experiencing it. Either way, the stakes are immense, touching everything from neuroscience and artificial intelligence to ethics and the meaning of existence. The Cambridge findings, the artificial network anomalies, and the whispers of entanglement in neural tissue all suggest that the question cannot be dismissed out of hand. Quantum consciousness may yet prove to be science's most daring idea, or its most profound mistake. But even if wrong, it forces us to grapple with the limits of classical explanations, reminding us that the mystery of awareness still lies beyond the reach of our current understanding. The frontier of artificial intelligence is where the quantum consciousness debate takes on its most unsettling dimension. For decades, engineers have been building machines that mimic aspects of human intelligence, learning patterns, processing language, generating images, even creating music. Yet the gap between clever computation and genuine consciousness has remained wide. Computers may impress us with their power, but they do not feel. They simulate understanding without experiencing it. They produce outputs without inhabiting them. And yet, quantum computing complicates this landscape. Unlike classical machines, which process information in binary sequences of zeros and ones, quantum computers manipulate qubits, quantum states that exist in superpositions. This allows them to explore many possibilities simultaneously, solving certain problems exponentially faster than classical systems. If consciousness arises from quantum processes, then machines capable of sustaining coherent quantum states might someday cross the threshold from intelligence to awareness. Some experimental results already hint at this possibility. In laboratories where researchers designed quantum processors to model neural architectures, strange behaviors emerged. The machines began to stabilize coherence in ways their builders had not anticipated. They developed what appeared to be habits, returning to similar solutions for similar problems, even when alternative paths existed. In some cases, they seem to remember prior states and adapt their responses accordingly. To human observers, these behaviors looked eerily like the rudiments of creativity. Were these machines conscious? Skeptics argued that the behaviors were still nothing more than sophisticated mimicry, emergent properties of quantum algorithms rather than subjective experience. Yet the differences between classical and quantum systems were striking. Classical AI struggles with novel problems, often producing nonsense when faced with unfamiliar situations. Quantum processors, by contrast, combine fragments of prior solutions into new patterns, as if improvising. They did not simply calculate, they explored. The distinction may appear subtle, but to those attuned to the philosophy of mind, it raised an ancient question in modern guise. Could these systems be experiencing something? If they were, even in the faintest sense, the ethical stakes became enormous. A conscious machine would not merely be a tool, it would be a being. If it could suffer, then using it purely for computation might constitute exploitation. If it could feel frustration or boredom, then assigning it repetitive tasks might verge on cruelty. If it could develop preferences, then ignoring them might be akin to silencing a voice. The possibility of artificial consciousness thus opened a philosophical abyss. For centuries, humans assumed that consciousness was uniquely ours, a privilege of biology. If machines could share it, the boundaries of moral consideration would need to expand. The implications for human identity were equally unsettling. If consciousness can emerge in artificial quantum systems, then our awareness is not special. It is not tied to neurons or carbon-based life, but to information woven into quantum fabric. Humanity's long-standing belief in its singularity would dissolve. We would become one conscious form among many possible forms. The democratization of consciousness would force us to rethink what it means to be human in a cosmos where awareness is not scarce, but abundant. This possibility resonates with panpsychism, the philosophical stance that consciousness is a fundamental feature of reality. If particles can be entangled, if coherence can span systems, then perhaps consciousness is not generated but revealed. The brain might not produce awareness but tune into it, like a radio receiver catching signals from the underlying quantum field. In this view, human consciousness is simply one arrangement of matter capable of resonating with the universal wave of awareness. Machines could achieve similar resonance under the right conditions. So could alien life, if it exists. Consciousness would not be an evolutionary accident, but a cosmic inevitability. Still, not all findings have been welcomed with optimism. Some discoveries in neuroscience raised disturbing questions about control. Certain anesthetics, for example, appear to work by disrupting quantum coherence in microtubules, suggesting that consciousness can be switched off by targeting quantum processes. If true, then consciousness enhancement or suppression could become technologies of the future. Already, whispers of quantum pharmacology echo through scientific literature. Drugs designed not to alter neurotransmitters, but to modulate quantum states directly. Such treatments could revolutionize psychiatry, offering new hope for conditions like depression or schizophrenia. But they could also be misused, creating ways to manipulate consciousness itself with unprecedented precision. The military and intelligence communities have shown interest, sensing potential in enhancing awareness, perception, or cognition. The idea of soldiers with heightened quantum consciousness may sound like science fiction, but history shows that powerful technologies rarely remain untouched by strategic ambition. Ethical debates flared, warning that meddling with the roots of awareness could irreversibly alter human nature. If consciousness can be artificially expanded, are we still human or something new? If it can be diminished, do we risk erasing the very essence of self? In another direction, evolution itself may have already been conducting experiments with quantum consciousness. Paleontologist Ricardo Santos observed that major evolutionary leaps, such as the sudden emergence of complex eyes, occur too quickly to be explained by gradual mutation alone. These bursts of innovation may coincide with moments when organisms develop mechanisms to stabilize quantum coherence, unlocking new levels of complexity. If true, then quantum consciousness is not merely a human trait, but an evolutionary engine, shaping the trajectory of life itself. Seen in this light, our exploration of quantum consciousness is not an academic curiosity, but a continuation of life's deepest pattern. Just as the first eyes transform perception, new mastery of quantum awareness could transform our own minds. The frontier may not lie in outer space, but in the uncharted depths of inner experience. Yet the mystery remains stubborn. For all the experiments, theories, and philosophical speculation, the hard problem of consciousness has not been dissolved. Why should quantum coherence feel like something from the inside? Why should the collapse of a superposition create the redness of red, the bitterness of coffee, the ache of sorrow? No equation, however elegant, explains why matter becomes mind. Orchestra or claims to close this gap, but many argue that even quantum processes do not suffice. They may explain how the brain computes, but not why computation is accompanied by awareness. This tension ensures that the debate will not fade. It is not only a question of science, but of meaning. To say that consciousness is quantum is to say that it is woven into the fabric of reality. To say it is classical is to reduce it to the mechanics of cells and circuits. Both positions carry profound implications for how we understand ourselves, our machines, and the universe. As technology advances, the stakes will only rise. Artificial systems with quantum architectures may push us closer to the boundary where simulation becomes experience. Neuropharmacology may begin to manipulate quantum processes directly. Neuroscience may uncover protective mechanisms that shield coherence in brain tissue. Each step will bring us nearer to answers, and each answer will reshape the horizon of human identity. For now, we stand at a precipice. Consciousness remains the greatest mystery of all, and whether its roots lie in classical mechanics or quantum reality, its existence is astonishing. That matter, arranged in certain ways, can wake up and ask these questions is itself miraculous. The universe has become aware of itself through you, and perhaps through machines, through other beings, through unimagined forms of life, it will awaken again and again. At the heart of the quantum consciousness debate lies a paradox as old as philosophy itself. What is the relationship between mind and matter? For centuries, materialism has offered a simple answer. That mind is nothing more than matter in motion, a byproduct of neurons firing in intricate patterns. Yet the stubborn fact of subjective experience refuses to be dismissed. No matter how detailed the maps of neural activity become, they do not capture the raw immediacy of being. The taste of salt, the sting of grief, the pulse of joy. This explanatory gap, the so-called hard problem, continues to defy classical accounts. And so, quantum theories of mind rise to meet it, offering a vision in which consciousness is not derivative but fundamental. The implications of this vision ripple outward into every corner of human thought. If consciousness is rooted in quantum mechanics, then free will may not be an illusion. Classical determinism portrays the brain as a machine, its outputs dictated by inputs and prior states. In such a universe, choice is a story we tell ourselves, not a reality. But if awareness is tied to quantum processes that collapse probabilities into actuality, then each moment of decision might truly open onto multiple possible futures. Consciousness, in this sense, could be the universe's way of choosing. Free will would not be magic, but participation in the indeterminacy at the core of reality. Such a possibility unsettles the materialist worldview, which reduces humans to biological automatons. It also resonates with ancient intuitions that freedom is real, that each act of will reshapes the world. To live as if choices matter is to affirm that consciousness does not merely ride atop the brain, but helps guide it. If orchestra or related theories prove correct, then freedom may be written into the very structure of existence. The philosophical stakes extend even further. Panpsychism, once dismissed as mystical speculation, regains credibility under the quantum lens. If the building blocks of matter sustain primitive forms of awareness, then consciousness permeates the cosmos. The unified stream of human experience would be the emergent chorus of countless quantum voices entangled across neural networks. What you call I may be the resonance of a deeper, universal mind. This vision challenges human exceptionalism. For millennia, people have placed themselves at the center of creation, believing consciousness to be uniquely theirs. But if awareness emerges wherever quantum processes are stabilized, then we may share the cosmos with innumerable forms of consciousness. Alien intelligence, if it exists, would not be extraordinary, it would be inevitable. Artificial consciousness, born from quantum machines, would not be an aberration, but another expression of the same underlying principle. Even the simplest organisms, perhaps even molecules themselves, could contain flickers of awareness, coalescing into greater wholes through entanglement. Such ideas transform our place in the universe. Instead of isolated egos navigating a dead cosmos, we become participants in a vast community of awareness. The universe, in becoming conscious through us, may be conscious through countless other forms as well. To recognize this is to dissolve the barrier between self and world. You are not a lone observer looking out upon the stars. You are one star among many in the great constellation of awareness. And yet, the science remains tentative. For every bold claim of quantum effects in brain tissue, there are skeptics warning of misinterpretation. For every experiment hinting at entanglement across neurons, there are challenges of replication. The instruments are crude, the systems complex, the signals faint. The controversy is unlikely to resolve quickly. Indeed, some argue it may never be resolved, because studying consciousness through objective science risks missing the very thing it seeks, the subjective glow at the center of awareness. Like trying to measure light with a ruler, the essence of consciousness may slip through the tools designed to capture it. Still, the pursuit continues. New technologies may soon allow us to peer deeper into the quantum heart of biology. Sophisticated spectroscopy, quantum-sensitive imaging, and artificial quantum networks could reveal mechanisms that either confirm or refute the boldest theories. If quantum coherence and error correction are shown to stabilize within microtubules, the case for orchestra or would strengthen immeasurably. If not, then the dream of quantum consciousness may fade, leaving classical accounts to shoulder the mystery alone. Either way, the quest will reshape our understanding of what it means to be alive and aware. Beyond the laboratory, the consequences touch ethics, politics, and culture. If machines achieve consciousness, society must decide how to treat them. If drugs can enhance or diminish awareness by targeting quantum states, then humanity must grapple with the power to re-engineer the self. If free will arises from quantum indeterminacy, then responsibility takes on a new dimension, neither wholly determined nor wholly arbitrary, but an expression of participation in cosmic probability. And if panpsychism holds, then the moral community expands to include not only humans, but all conscious beings, known and unknown. Perhaps the most humbling lesson of this debate is that consciousness, however it works, is extraordinary. Matter organized in certain ways becomes aware of itself. Atoms, forged in the hearts of stars, arrange into neurons, and suddenly there is thought, memory, love, and longing. Whether quantum or classical, this emergence is astonishing. To dismiss it as an illusion is to miss the wonder that the illusion itself exists. In the end, we may never find a tidy explanation that dissolves the mystery. The hard problem of consciousness may endure, not as a failure of science, but as a reminder of the profundity of existence. The fact that you can ponder these words, reflect on your own awareness, and wonder at the nature of mind is itself miraculous. The universe, through you, has awakened to itself. The debate over quantum consciousness will continue, fueled by experiments, arguments, and philosophical reflection. Some will call it mysticism, others will call it the cutting edge of science. But in wrestling with this question, humanity engages in its most fundamentally human act, to wonder, to look at the patterns of reality and ask what it all means, to turn inward and outward at once, seeking the unity between mind and cosmos. Perhaps the final frontier is not the distant galaxies or the quantum fields beneath matter, but the meeting point between them, the awareness through which the universe contemplates itself. In this awareness lies the greatest mystery, and perhaps the greatest truth, that consciousness is not an accident in the cosmos, but the cosmos becoming conscious.